Steve Whetstone, thank you for sharing free information, knowledge and wisdom. I have been number pirate shipping. Share your videos in Facebook groups for number Electric Universe and number S4ECC 2048.
a mineral like any other mineral? Is that how it what would you say? How did it? What's the
And
origin of?
is
A mineral like any other mineral? Is that how it? Is that how?
This is a video for Kathy Castor, for members of the House Select Committee on the Climate Crisis seeking to delete this channel from YouTube and others for offering alternative climate discussion. This is a video for all politicians, for the CEOs of YouTube and Google, and most importantly for all of you. Most people think there is climate and denial.
Steve Whetstone, thank you for sharing free information, knowledge and wisdom. I have been number pirate shipping. Share your videos in Facebook groups for number Electric Universe and number S4ECC 2048.
The elements are the building blocks of everything we see and know around us. Conventionally, we are taught
this presentation some things that have happened over the last week which have resulted in a slight adjustment of priorities, let's put it like that. And I also have some incredibly beautiful data to share at the end of the presentation as well. So stick with me for that. Anyway, it's good to see you. Yes, fantastic, you can hear me. So this is Tree of Life Part 1, and this slide has a image which is a panel. I think it's from Iraq, from the sort of Sumerian art sort of lineage, and it's I don't know whether I'm going to say this correctly, but it's a Phrygian panel closely following the Sumerian Tree of Life, and apparently this is from around 600 before Christ. So if Christ was able to go into the desert for 18 years of his life in this region, could he have learned some of the tricks of the trade from these people? Who can say? It's the 23rd of May 2020, and I am going to try and talk about how exotic vacuum objects can actually do real work. And there is a lot of interest in being a multi-planetary species, and I believe that that's what we already are. But anyway, if we are to go to other planets, we are going to need to be able to ensure that when we get there, we have all of the elements for life. Well, we have all of the energy when we get to a planet because it actually has matter on the planet. But can we use that matter and convert that into elements that support life? And if you have water there, well, I would argue that you can, because from water you can create a charge differential, and from that you can create other elements, and with other elements you can create electricity, and from electricity and other elements you can create all the elements for life and more. And so I think I'm going to start that argument here. The actual image that you see here, this panel, is something I took off a slide which I had in my Sochi presentation, because it's actually from a slide from Ode, and this was one little element that I left out, which you'll see the full original slide from Ode in this presentation. So what am I going to talk about? Well, firstly, I'm going to talk about the fact that carbon actually is quite a rare element. So if I get rid of my mugshot there, if you look at the Earth's crust, that is, if we start with the Earth's crust, and we look at the elements here, and I'm going to go back to my mugshot, and I'm going to change my mouse so you can see me pointing. Let me just do that. I should have done that before. Preparation prevents poor the other one, and we'll do that. And we'll put the silly large cursor. Okay. Right. And we're back in the presentation. So we have a big cursor here. And now, if you look at the most abundant elements in the Earth's crust, well, top of the list are oxygen and silicon. And in fact, they account for, let's put a quick calculation here, they account for 40, 50, 60, 72 point something, 72.3% of all of the nucleons in the Earth's crust. And then aluminium, who everyone worries about as being something that's really rare, well, actually it just binds to oxygen really, really well, so it takes a lot of energy to produce aluminium. But actually it's the third largest concentration element of abundance in the Earth's crust. And if you add that to your 72.3%, you get 80, over 80% of the crust is these three elements, O, Si, and Al. Add in iron. Now, of course, iron is more in the core, but we're talking about the crust here. That's the bit we live on. Fortunately, we don't live in the core. That would be uncomfortable. And then if you look at these other elements here, calcium comes in at number 5. Okay, and this is going to be relevant as we go through a discussion moving forward. But obviously, you can't have bones in your body without calcium. Oh, that's my mess there. Would you look at that? That's a treat for you. You can't have your body bones, and you can't have calcium carbonate. You can't have seashells. All kinds of things rely on this incredibly abundant element here. And calcium is double magic. It has 20 neutrons and 20 protons, which means it's extremely stable. So if anything was to transmute to calcium, it's unlikely to transmute away from calcium, or it's less likely. So we actually find calcium in many, many linear reaction systems, and I believe the crust is a good way to know that it is something that we should expect. And that is, again, 4.15%. So in terms of the crust, calcium is bordering on very close to the amount of iron there is in the crust. And so it's very likely element, in my view, to be created by exotic vacuum objects. Then, of course, sodium is important, as is potassium in our blood for, we're a saltwater creature. We don't live in the sea, but our blood is basically salty, and we have salt in the form of sodium chloride and potassium chloride. Magnesium here, we see all of these elements often produced in low energy nuclear reactions. And hydrogen here is actually, it's quite the way down the list, and considering hydrogen and oxygen up here are so important for life, then why is this down here? Well, basically hydrogen is a building block, and you'll see this as we go through this presentation. And phosphorus is very important to life as well. Manganese less so. And then we've got down here sulfur, very important to life, and there is carbon at the bottom of this list. And look at the proportion here. It's 0.02%. 0.02%. So, when you compare all the other elements above it, this is a relatively rare element. And so, it's a precious resource, and people think of carbon dioxide as a terrible thing in the world. But actually, if we didn't have carbon, we couldn't exist, and neither could plants. And so there we go. Right, so where is all of these elements coming from? Well, if you were to look at the public data on this, there are two things that are going on supposedly in the sun, and one is the carbon, nitrogen, oxygen cycle, and the other one is the triple alpha process, supposedly. Okay, and we're going to read this little clip here from Wikipedia. This is the official accepted understanding. Unlike the proton-proton reaction, this is this pp chain up here, which consumes all its constituents. The CNO, or the carbon, nitrogen, oxygen cycle, is a catalytic cycle. In the CNO cycle, 4 protons fuse using carbon, nitrogen, and oxygen isotopes as catalysts, each of which is consumed at one step of the CNO cycle, but regenerated in a later step. The end product is one alpha particle, a stable helium nucleus, for those that don't know, and 2 positrons and 2 electron neutrinos. Now, what you have here is the so-called log T. This is the temperature, and this is the log energy that you get out. And the sun apparently is about here. And it's just at the bottom end of the CNO cycle. And so the theory is that we only see the CNO cycle very little in the sun, and apparently it's something like 1.7%. And in fact, I'm led to believe that last year they detected the electron neutrinos supposedly coming from this process that shows around about this supposed 1.7% of the sun's energy being derived from the CNO cycle. Of course, if you had a process that didn't actually release so many neutrinos, these electron neutrinos, because it was actually working in a different way, and you may not even have, a safe understanding in terms of. You might be assuming that this is the process, and you're seeing something akin to the amount of neutrinos you would expect coming from the sun, but in fact the process is wrong, and in fact it's just working a completely different way. But let's assume they're right. The triple alpha process is all the way over here, so the idea that you're going to get much triple alpha going on is not really something one would expect. And what do I mean by that? Well, the triple alpha process is where you get 4 helium nuclei basically merging to 1 carbon-12. Well, this is interesting because we see this all the time in LENR. And why would this not be part of LENR as well? If we could rapidly get to carbon, okay, then we start off with carbon, which is the true catalyst, along with 14 nitrogen in the CNO cycle. And if you add a proton, you release a gamma. But if we're in an EVO, the gamma wouldn't get out, okay? And that would go to 13 nitrogen, which is unstable. But because it's in a EVO, you have neutrino processes, not you get maybe an antineutrino or something coming in, and it works the other way. Rather than a positron, it takes an electron on board. And you go to 13C. I think I've got that right. I might not have got it right, but this is unstable, and so is the oxygen 15 here. This is not normally seen in nature. 14 nitrogen, 13 carbon, 12 carbon, and 15 nitrogen is normally seen in nature. And so that's why you have this decay here. Okay, so essentially you go around in a loop, but what we are finding in low energy nuclear reactions is that whatever goes into the system, you seem to get a lot of carbon out and then other elements. So it doesn't actually matter if you start with heavy or light elements. And over this and the sister presentation, I think you'll see data where you can pretty much conclusively say that is what's going on. And then that draws into question whether the sun is actually working in these ways. I mean, it seems very nice, but what is driving this argument? Driving this argument is this fantastic temperature. You need the temperature in the center of the sun to do the PP chain. There's very little CNO, and then this is for just different stars. If you are going to get these reactions going on in abundance, there has to be a different process, because the log T needs to be so high to cause this triple alpha process. I don't think it needs to be. I think the idea of smashing things together kinetically, and the low probabilities of them having the right energy and being able to get through the Coulomb barrier and located, I think it's probably all maybe a misunderstanding. I think if you can get them coherent and you can remove their electron, the electrostatic repulsion from them, and get them close enough together through this coherent matter, you could have this process of production of carbon in a much less energetic way in terms of kinetics, and it's kind of like it's doing it the implosion way rather than the explosion, massive kinetics way. And I believe that this could possibly be one thing that's going on in the sun, because we see it in low energy nuclear reactions. So let me go on. So I shared this. This is ODE slide 11. Actually, it's the full ODE slide 11 because it was missing this when I used this slide in Stanford in 2017, because this was from the work I did with the George Oshawa cycle. and when I was preparing to run the supernova reactor, which you can see here. So it's this George Oshawa slide, and it's the carbon arc in air reaction. Okay, so I'm going to drop my mugshot over there. And so you have the primary sort of CNO cycle here. You can see the CNO cycle here. So that's kind of there. And what I've listed here is the naturally stable isotopes. And this guy, George Oshawa, he developed the macrobiotic diet. But what he also did is he found that if you took 2 carbon rods in water and you discharged, I think it was like 3 12-volt batteries together underwater, you were getting all of the elements that you see here. And the interesting thing is that Sundaresan and John Bockrus here, they found that if you didn't have oxygen dissolved in the water, and I've said that this is very important, oxygen. If you didn't have oxygen dissolved in the water and you replaced it with nitrogen, you didn't get the ion production. So rather than this reaction where carbon and nitrogen, this could happen in the air, produces aluminium, and this, I believe, was observed by an HHO researcher called Slobodan Stankovic in Switzerland, in Swiss Hydro HHO Energy. You take 2 aluminiums and you fuse those to iron 54, and we kind of see this production of iron from 2 aluminiums potentially in John Hutchison systems and other systems where we're using aluminium, if you remember from the recent experiments using ultra. So this is one pathway where you can get to iron. But there is this other pathway that John Bockrus, and John Bockrus was one of the world's greatest electrochemists, and he took on board this study by George Oshawa, and he found, working with Sundaresan, that when they had oxygen dissolved, they get iron. And so this is the process that we're looking at. 2 carbon 12s, and 2 oxygen 16s goes to iron 56 and helium. And the interesting thing is you can actually synthesize. What you're looking at here is, I think it's something like, I did calculate it before, and off the top of my head it's somewhere between 98 or 99, or maybe even higher, but certainly higher than 98% of all of the element nuclei in your body. So essentially what I'm saying is that if you start with carbon and electricity and water, i.e. you've got hydrogen and oxygen, the hydrogen gets you to go round this loop, the CNO cycle. The oxygen can easily get you to iron, which you need for your hemoglobin, absolutely important, so that you can transport your oxygen and your carbon dioxide in your body. And so that's absolutely important to have the iron. And if you then have hydrogen, that takes you round there. The oxygen assists with that. And with the electricity, you combine these together. So, for instance, carbon and carbon goes to magnesium. There's the phosphorus we need. Silicon's everywhere, so there's all kinds of paths to silicon. Aluminium here is like one of the main paths, and silicon is one of the main paths. So it's not surprising that oxygen is the most abundant element in the Earth's crust, and silicon is the second most abundant element in the Earth's crust, and aluminium here is the third most abundant element in the Earth's crust. The interesting thing is phosphorus is not that abundant. It is quite an abundant element, but it's not that an abundant element. So it's almost like elements get stuck here and they get and here, and this is not surprising because these are quad alpha and tri-alpha. Okay, so I talked about this because one of the main reactions you see from ball lightning, and I talked about this in Stanford on the 25th of January 2017, is this sulfurous sort of smell you get at the end of a ball lightning exploding, and that would be, in my view, oxygen and oxygen fusing together. And we observed this production of sulfur, it would seem, from oxygen that was on the top of copper, in the 10 yen coin that was exposed to Amasa gas, and we saw them as snowballs on cobblestones. Anyway, so this is the George Oshawa cycle. So starting from essentially protons, you can build this up. And in Lena, it would appear that if you have just hydrogen in there, you can end up by synthesizing, certainly hydrogen and oxygen, you can end up synthesizing carbon, and we'll talk about examples of that. And with the carbon and the hydrogen and electricity, you can then go ahead and synthesize pretty much everything for life. So this is really about the process of terraforming. Now, when did I see the first production of carbon in a form which was very interesting in a Lena system? Well, I'll tell you, that was with the the experiment by Celani, and this was a Celani wire we had run for a little while. And on the Celani wire, we had these nano and micrometric diamonds forming. And it was this particular image that was taken in May 2013 by Matthew Velat, a former director of the MFMP. This was the image that inspired me to suggest in that, around the spring of 2013, that people use nickel and diamond as a potential reaction matrix for doing low-energy nuclear reactions. And it was the Lion experimentalist who was the first experimentalist to consider that. And actually what you're seeing under here is constantan wire, and this is actually made of nickel and copper. And so there we have that. And then so this was the first experience that I had of carbon apparently being synthesized. I mentioned something in the monopole clutch, and that was about Yule Brown's radiation remediation. And I've got a link here, and you'll have the slides here so you can find this data. And essentially, he said this was a reference about Yule Brown's work. And it says, the most startling claim by the inventor, and this is in his patents and in some of his writings, the most startling claim about the inventor in the press is that the gas produced in his process can reduce nuclear and toxic waste to harmless carbon. And that was in magazine in 1988. 1988. This is even before Pons and Fleischman. This is being reported, and I believe this is in his patents and in some of his writings. So yes, this is producing carbon, okay? And this is just the rest of that slide where he's remediating some waste. So what did Takaaki Matsumoto conclude in the final sort of summary of his research that he gave as a brief note, as a letter to the editor, I believe, in 2001? Well, it was this. My three-ring traces were products of those simultaneous explosions. Here, I have to apologize to the readers for an insufficient assignment made in reference 5, that quad neutrons collapsed. It was made clear by later experiments that the clusters that collapsed were atomic clusters that could have a diameter of hundreds of micrometers and involve much more nuclei. Well, I would imagine that an atomic cluster that is hundreds of micrometers would necessarily involve much more nuclei than 4 neutrons. Very amazingly, it was also found later that the ring products consisted of conventional elements, mainly carbon, not dependent on collapsed materials. This process was called by him nuclear regeneration. So here we have the summary in 2001 of the findings of Takaaki Matsumoto was that it doesn't matter what you put in, you get carbon out. And here it is a claim by Yule Brown in as reported in Imagine magazine in 1988, that it doesn't matter what you put in, you get carbon out. What are the chances? What are the chances? And what do you have in Brown's gas? You have a highly energetic process with at least very intense electron exchanges, and you have hydrogen and you have oxygen. What am I saying you need? You need hydrogen, and well, if you start with water and you have electricity, I believe you can be well on your way to making the sort of terraforming and making the everything you need for life. Okay, so what I'm showing you here now is, well, when I will, is the actual slide from the 4th of October 2018, but the real slide that I modified for that presentation, Seek and Share in Sochi, which is O-Day slide 52. So I'll show you that now. So it's called a Sumerian Tree of Life. And what we have here is something from 2017 from the Lion 1 inside of the quartz core. And you see something here that's bleeding out and deposits something here. It comes over here, pauses, comes over here, pauses, comes around here, pauses, comes round, pauses. And it's kind of leaving a trail behind it. It's like a vine. It's like a vine, and then it ends up with little flowering points along it. This is Shoulders from 2004. And you can see as it goes along, it has little branches that come off, and they come to endpoints. Okay, and this is from August the 8th, 2016. This is the Moscow Nuclear Physics Institute, and what you're looking at here is tungsten, and this is tungsten on the inside panel of a tokamak. Okay, so what you want is something that is supposedly good at dealing with high temperatures on your inside of your tokamak. You want to keep the plasma core confined, but there will be some radiation of heat, and there will also be some diachron instabilities, some Poincare instabilities, some all kinds of fluid dynamic instabilities in there that seem to come together, and they shoot off these things. I wonder what they could be. Anyway, they hit the wall of the reactor, and the kind of thing that you see are these, and they call them snowflakes, and they call them monopolar arcs, and you can go and read about it by following this link after the presentation. And you can see that you have a very similar thing, and it's ending up by these black areas. And what have I shown you? Well, I've shown you in other presentations that low-energy nuclear reactions can eat tungsten for breakfast, and when you are looking at an SEM like this, something that is darker like this is typically a lighter element. So if this is tungsten, could this possibly be oxygen and other alpha conjugate nuclei? I would imagine it is. So I believe what you're seeing here is the kind of equivalent to this, the kind of equivalent to this, and the interesting thing is, at the end of these, you have the fleur-de-lis, the little fruiting bodies on there. And it's almost like the actual process of what an EVO does is analogous to what a plant does. It's like the same thing, but on a different scale, where you have at the tips of your plant, you typically get the fruit, the flowers, and then you get the fruiting body, and that's where all of the sweet nutrients, all the good elements and compounds are placed. And it's like EVOs in these are definitely EVOs. I would almost certainly say that these are EVOs, but the products that you get from whatever you give it are the things that are best for life. And I believe that what he is saying here supports that, and I believe what Yul Brown found in the 1980s supports that too. Okay, so a couple of other examples before we start showing you some other data that has been seen, that was shared earlier last century, but it's going to be the first time you guys see it. This we've talked about quite a bit. This is also from the Moscow Nuclear Physics Laboratory. So it's MEPHI, Moscow Engineering Physics Institute. It's the National Research Nuclear University. Okay, and so this is a plasmoid that was found 2 days after an electrical discharge onto a metal plate. and there's no electricity on there. It doesn't matter whether it's grounded or not. This is floating around and doing something. Here's something similar on the Hutchison bull burn sample, an aftermath from the bull burn sample from 1986, which I discussed at length, and we found that this we have observed at 2 orders of magnitude on different Hutchison samples. But what I'm going to talk about again is this over here, which I believe is going to be very relevant to the tail end of this presentation when I make the argument about how potentially this is going on. And we'll have a closer look at that now. And for some reason I've got the same slide in there twice, but okay, so what we are looking at here is what you've just seen, but under the color microscopy. And we have something in here which is a sphere of something, and it could be silicon, oxygen, and carbon. And if it is, and then all 3 of those elements are alpha conjugate nuclei. So let's investigate what we see, and we've seen this before. So we are looking at here with the SEM, and here if we look at this area here, 61, we see that it is carbon 60% of the atoms are carbon. 33% of the atoms are oxygen. So this is in the CNO cycle, okay? And what did I say? It looks like N doesn't hang around for very long, okay? Well, why is that? I don't know. But if you don't get phosphorus because N doesn't hang around very long. Well, if you go back to the carbon, the CNO cycle, actually here, what did I say? Well, the oxygen here is not stable, and the nitrogen here is not stable. This is that relevant? I don't know. But I think it's more like is being described by Matsumoto. It's all happening at the same time in the collapse. Okay, so we've got essentially between triple alpha and quad alpha, we have 93.4% of the matter in that area. Now, if we look at the flat area over here, spectrum 60, we have over here it's just a 2.1% atom percent of iron. Over here it's 10.1% because we're on the flatter area, so we're actually looking at the top surface of the iron. But it is this affected area by this exotic vacuum object, in my opinion. And we've still got 64%. In fact, that's more carbon on that area there. And we have oxygen here. So between them, that is about 83%. So it's about the same ratio of alpha conjugate nuclei. And then we have iron. And, well, what is iron anyway? Well, iron is, according to Sundaresan, it's a combination of carbon and oxygen anyway. So, you know, they're all the same thing. And then the chrome and the nickel, I imagine, are from the steel. And we're seeing these other elements here. Sulfur, silicon, aluminium, potassium, calcium, chlorine. These are all the things for life. Again, what do we see over here? We see iron, aluminium, chrome is in the metal, sodium, sulfur, silicon, chlorine. So these are many of the elements that we saw being synthesized from the George Oshawa reaction tree. Okay, now I believe that what is going on in here is this is where this so-called nuclear regeneration occurs. The self-compression, the nuclear collapse process is going on in this area. And when I show you some absolutely stunning data from Takaaki Matsumoto, you may or may not agree with me in light of what we've seen in Vega experiments. Okay, so again we're looking at this, and I just wanted to point out this is the Kanthal heater wire, and for whatever reason we got these counter-rotating vortices, and something came out of here, around here, and went into this wire. But the wire itself is made of iron, chrome and aluminium. This is fused quartz. It's silicon and oxygen. And this is an aluminium oxide, Al2O3. So if we actually look at what we see on there, and we've shared this before, we have an impact of something at that point here, with a central point, and then this kind of like crystallites around there. Well, what were the crystallites? Well, the crystallites look like this, Okay, and they are kind of hexagonal or pentagonal in structure, so they're like little tubes which are hexagonal. Okay, and I'll just remove my mugshot so you can see the accretion on the heater wire. Okay, and there we go. And so the Kanthal A1, which is the heater wire itself, its nominal composition contains between 0 and 0.08% of carbon. Okay, and then you've got your chrome is about 20.5 to 23.5, 5.8% aluminium, and the balance is iron. Okay, so what do we actually see in these crystals? We see by, I think it's by atom percent, but anyway, 29%, like virtually 30%, 29% is carbon, no, and 65% is oxygen in these, whatever they are, okay? So, again, we're seeing something here which is around about 84% of carbon and oxygen, which is remarkably similar to the kind of 83% we're seeing here and 83% here, okay? Synthesized by this exotic vacuum object. Then we have aluminium, which is in the Kanthal. There's some silicon, so there's actually between 0 and 0.7%. Well, 0.46% is between 0 and 0.7%, so that's not a surprise. Chromium seems to have disappeared. Very little chromium, but then this is a deposit on the top. Iron's there, but what we can say is it has aluminium, it has chrome, and it has iron. So, yes, there is something going on here which is like Kanthal, okay? However, where is this calcium coming from? We have 1.69% calcium, and if this is by percent, atom percent, that's actually quite heavy because these other elements are quite light by comparison, okay? So we have a lot of calcium. This DEC alpha, as I call it, 10 alpha.
Then we will take a look at some incredible cutting-edge research from
it's a
scientists
conjugate
at IBM.
nuclei of
This is an
basically,
atomic
if you
force microscope
bunch a whole load
image
of
of
these
the-
together, you end up with this. Okay. Now,
We see at work
I
here
talked
is
about
what I
at the
believe
beginning of the
would truly be
presentation
defined
how
as the strong force.
once you've got these basic building blocks of alpha nuclei, and alpha itself forms helium, and that floats away as a gas, and you get lost that. So if you make 2 alpha and bring them together, I've talked about this before, that forms beryllium-8. Well, what happens is that decays extremely quickly to 2 alpha, and they float away. So the first alpha conjugate nuclei you can get is triple alpha. And so if you're going to build the other building blocks for life using this technology, forget what the sun's doing or a supernova is doing, using this technology, you need carbon, okay? And hydrogen and ideally oxygen and electricity, as I've argued before. But anyway, we can see that it appears to be making the carbon and oxygen, and if we've already got water, then we've got what we need to move forward. Now, what did Leclerc say? And now, it's very sad because these things get taken off the web. So this is actually another slide from O-Day, the full slide. I shared something similar, I think, in my Sochi presentation, but it didn't have this extra bit on here. And I was talking about lead here. Now, lead is important, and I've argued why lead is important. So this is Leclerc. He's a researcher who looked at cavitation, and his company at the time was called Nanospire. And they found that by using water in a PVC tube and spinning it round with a piece of aluminium that had holes in it, he would create every element in the periodic table here in a stellar sort of distribution here. In fact, it's stellar up to here, and he's got iron up here as the end point of your stellar nucleosynthesis, and note calcium is higher. And then this is supposedly supernova synthesis. And then this, from lead onwards, is happening as well. Okay, so you've got uranium, polonium, californium, and all kinds of americium here. So I actually believe all of this can be accounted for with exotic vacuum objects. It's just you're driving it too hard when you're going up here. When you're going up here, you're getting some of the things that S.V. Adamenko saw. Okay, but the interesting thing is you get a lot of lead. Now, lead is actually very, very abundant in the Earth's crust, often with sulfur, lead and sulfur. And so that is very interesting. It's also found with often tin, which is right in the middle. So if you had an element over here and it's trying to do this averaging process with lead, you would end up with tin, wouldn't you? Okay. So there we go. So anyway, so we got lead. And the interesting thing about lead is it's actually the most heavy, or the most nucleons you can get in a nucleus without it becoming unstable. In fact, bismuth has a very long half-life, but it is actually unstable. So lead, if you wanted to test Leonard's capability, you would choose lead, okay? You would see what would happen if we started with lead. Now, the other thing is, what I'm saying about carbon being your building block is that if you do have a system where you have a lot of carbon and you're driving it with your exotic vacuum objects very hard, you must first get rid of 55% of your carbon, according to the work of Leclerc. So you must drive beyond carbon to so that your carbon drops below 55% of the reaction matrix, and then you can start synthesizing iron and heavier elements. And guess what he's saying? It goes in alpha steps. This is alpha conjugate nuclei. So my realization that it needs alpha steps is one thing. But this was actually in the 760-page book by S.V. Adamenko that he published in 2006. So it wasn't an original idea, but it was the titanium that was exposed to a Mars gas where we had polytetrafluoroethylene, Teflon, and we contacted the two. There was an explosion, and then we saw these what Solin called quantum coherent crystals forming with their gaps between them. And on some of those there were these spikes, and on the spikes you had basically nickel, then iron, then I think it was chromium, and then titanium, something like that. And these are alpha steps going on, and then at the end, when it ran out of titanium plus alpha conjugates, it then ended up with just the carbon left, or the alphas, and it just dumped a spike, a carbon nanotube coming off the end. And so in that experiment that we did with Roy Shinamaza, we showed this progression of how the exotic vacuum object is able to synthesize heavier elements, and as it kind of runs out of steam, it just dumps the remaining carbon payload, which might mean that you have to, exactly what it's saying here, it's one is speaking to the other, that you have to get below a certain amount of carbon before you can start creating much heavier elements, because it will always synthesize things down here, which are actually most of the elements for life, and most of the elements that you actually stand on or sit on or breathe. The actual main useful elements for life. So I have a link here to the YouTube where he's discussing this, but like I say, it's been taken down, and that is just the nature of these things. If you want things to persist, you have to make a copy, and that goes for this channel as well. So thank you all those people out there that have taken it upon themselves to clone this channel. It's very helpful. Okay, so how does this fit in with Takaaki Matsumoto? Well, in the last presentation earlier this week, I shared a couple of slides that he
Hello everybody,
made public
and welcome
in
to Ancient Architects.
at the
Please subscribe now to get the latest ancient history news and independent research from around the world.
And in that, it had
situated next to Cusco in the Inca heartland of Peru,
magnetohydrodynamic structures in there, analogues of which and exact, I think, versions of which we've seen in a range of systems. So I discussed that earlier in the week, and so I'm going to show this slide here. That we had earlier in the week. So, and again, what I'm going to show you are, again, more SEMs from these simple experiments that he conducted, where he took either potassium hydroxide or cesium carbonate and had 120 volts AC, and he was pulsing those from between 20 milliseconds to 800 millisecond pulses on with a 20-second gap, and then a number of shots. Okay. The interesting one here is this is one long shot of 800 milliseconds with 20 seconds off. I don't know what that means because there is not more than one shot, so it's off for at least 20 seconds. Let's put it that way. And then we got one shot here. So this is what I'm going to be drawing these from. And what Takaaki Matsumoto did is speaks to what I have been talking about here, that many researchers, ourselves included, with what we've looked at, the LENR systems do like to top out at lead. And it's kind of like you've got a couple of hard stops. Iron is a hard stop, carbon is kind of a hard stop, and lead is a hard stop. And if you have anything lighter, it kind of works within these bounds. And when you understand the sort of nuclear relationships and so forth, it makes sense as to why this is happening. Anyway, he chose lead metal wire for his electrode diameter of 1 millimeter. Lead. That is very important. This is Takaaki Matsumoto in 1997 recognizing that if I want to know if this is able to synthesize something other than what you put into the experiment, let's start with lead. And if we have lead and we have potassium hydroxide in water, well, we don't have any carbon, do we? Well, isn't that an interesting thing? So I'm going to show you, it's a selection, there are many, but a selection from these various experiments. I've not included, well maybe I have, I think I've included some from the 72, but this actually has carbon in it, so it's a less of a good argument. And he recognises that. This is a lead sphere that is produced in the experiment S70, okay? And this one is S70 CDA, okay? So eruption of carbon film from a lead ball. So up here, on what may or may not be a pole, you've got a plume of carbon coming out. Well, is that carbon, like as diamond, as was observed by Leclerc, as was observed by us in our Chelani wire in 2013? Is this diamond? Is this diamond like we observed in the center of the cavitation spot in the Amasa vibrator plate? Could be. I don't know. But if it is, it must be amorphous diamond. And it's flowing. What would make that happen? I would think exotic vacuum objects would. And if this is a mesh, a supercluster of exotic vacuum objects, it's kind of like you've got a bleed out here. Now, is this the surface peeling off and coming up here? Or is it something inside that's bleeding through the magnetic pole of the
is buttressed by the existence of such a similar gas giant
But what you see here is Takaaki Matsumoto absolutely nails it, because he says systems of experiments S70 and S71 were perfectly carbon free. So he knows he's choosing lead for a reason. And he knows that when you have carbon coming out of here in a plume, this is something that had to have been synthesized. And if it's coming from the inside, is it coming from the inside? Well, that is interesting. So, the next slide I'm going to show you will be an almost one-for-one match to the plume that comes out of a volcano. In fact, several plumes are very, very similar to this. It's uncannily exact. But there's one that's a dead ringer. When we took a Mars gas and we exposed indium to it, just for 5-10 seconds or whatever. I will show you that in part 2 of this presentation. But let's see what Takaaki Matsumoto observed in his experiment that he conducted in 1997. Here it is. I don't actually know whether this is the lead ball or what, but he is saying that, and this is 72 BCH, so 72 BCH here. Eruption of carbon film from lead ball. Well, this is the ball. So this is a lot of material. Okay, so lead is 204, 206, 207, 208 nucleons, and carbon is just 12. So if there was stuff spewing out of the center of this, and it was a superfluid, and it's producing this almost like a volcanic cloud of carbon, that is a lot of material that is somehow being spewed forth, and the sphere is keeping its shape. This is not true of all of the structures that he has, and I will share those in coming presentations. But I can tell you now, you will see something absolutely nigh on identical to this when we look at the data from the Amasa gas exposed indium. Okay? So this still doesn't tell me if it's kind of like wrapping itself off the surface of the lead, or if it's being spewed out from the center. Okay? So let's have a look at the next slide, because this is absolutely completely descriptive. This
the magnetic
is an eruption. This is 71 BDB. Now remember, 71 and 70 do not have any carbon in them. Okay? 71 BDB, and we have 71 BDB again. This is a close-up of it. And we have a hole.
A regra da mão direita magnética roda no sentido da mão direita. Agora troca e Coriolis principal.
Like a little volcano. It's absolutely madness. Look, it comes out and it's spewing out. Okay? Now let's go back to our slides up here. Is this a kind of 50% in the quartz, as these ball lightning tend to do? They're half in and half out. Okay? And as it's traveling along, maybe it's spewing out carbon from the back end. You know, is it? I don't know, but that's what you're seeing. And at the end, when it dies, it dumps its whole payload. It just, the whole containment fails, and it dumps the lump. Is that what we're seeing here? Is that what we're seeing here in August the 8th, 2016 at the Nuclear Physics Research Center in Moscow? I don't know. Is this, and you'll see similar structures from Matsumoto in this same series of images he shared of electronuclear collapse processes, which do look very similar to this. And I believe that you have many EVOs that are coming down and hitting here and building up this layer on here. Okay? Anyway, so we'll come back to that, I think, in a future presentation. But let's go back here. So we have a sphere, and out of what would appear to be a port, it looks like a crack over here, maybe a crack here, but it's actually just coming out of here. Now, is it the case that inside this lead sphere was an exotic vacuum object like the spheres that we see in the Vega experiments, okay? And that on the coherent matter layer in there, where you've got the degenerate electrons, and they can't go anywhere, okay? They're as compressed as they can be. And what's happening is the lead ions in, being synthesized by the electrical discharge, maybe they are coming to the exotic vacuum object, and they are building up on that layer, and on the coherent matter layer, as the lead ions are coming in, okay, it's converting them into prima materia. It's converting them into the mother of all matter. It's converting them into this quark soup, let's say, this electron nucleus macrocluster, as S.V. Adamenko would say. So and they've completely denatured, just like the actual coherent matter. It's all coherent matter, and more lead's piling in from the outside. And what you are seeing is what you're seeing. My question is what you're seeing here the lead shell on the outside of the coherent matter sphere? And then as this breaks away, that through the pole there is just a spray of the lead and whatever else accreted to the coherent matter being converted into triple alpha. Is that what you're seeing there? I don't know, but that's a hypothesis. This is actually a very simple experiment. Hopefully, the question has been asked a few days ago in a letter to Matsumoto. Hopefully we'll have the details of how to do this experiment. This is not actually a very small structure. This is 25, it's probably, I don't know, it's about 50 microns across nearly, or less, well, certainly 50 microns from the end of that plume to over here. Okay? So, is what's coming out of this hair an amount of nuclei that used to be lead? Because there's no carbon in it to start with. And so it is a nuclear regeneration going on. And would this explain the hollow balls that were observed by various Russian researchers like Godin in the Vachayev replications? The Vachayev experiments are like, you have two copper electrodes, you have dirty water going through, and he gets all these metal balls being synthesized. And I understand, I think that they're hollow. And also Anatoly Klimov in his swirl, in swirl or inflow swirl reactor, he has a Tesla coil, he has an anode made of various materials and a cathode. And he does like discharges, but he ends up with these little spheres, and the spheres are hollow. I am arguing that the coherent matter structure forms that gathers matter that is in the process of being converted into prima materia or protomatter or electron nucleus macroclusters, or whatever you like to call it, mother of all matter, and that then the whole thing can collapse if it's not got too much on the outside, or the inside collapses and through the pole, maybe this is the North Pole. Maybe this is the North Pole. Maybe when you are looking at this is the South Pole, this is the North Pole. This is a subquanta, this is the North Pole, sorry, South Pole, this is the North Pole. So at the South Pole, you can imagine it's sucking matter in if it was available, but actually, it's actually coming from everywhere, maybe. And at the back end, it's ejecting matter. And I described this using in my Sochi presentations. It kind of like goes, and when I'm doing my silly noise there, I'm hypothesizing that it gets to an unstable state and it ejects some matter. And is this a way in which this can be used for propulsion? I don't know, but maybe it can be. Okay. So let's go back to that slide. So this, for me, explains these hollow spheres. I think actually Slobodan Stankovic observed the production of hollow spheres as well. In fact, he showed slides at ICCF 22 where you had spheres within spheres within spheres. So you can imagine that a sphere forms and then it becomes inactive, and then coherent matter forms on the outside of that sphere using it as a template, and then more matter comes in, goes around the coherent matter, and then that becomes inactive, and then it comes back and it does it again, so you end up with spheres within spheres within spheres. So that is my hypothesis for how Slobodan Stankovic observed those structures in his HHO exposed carbon. Okay, so now the next thing I'll show you is it says here generation of carbon films, and we are going to see this again in the indium, but we've seen carbon films in various experiments that I've shared over the last year or two, but we are going to see ones where Matsumoto has a sketch. I think it's a sketch or an image in his book or whatever. And there is a carbon film, well, it's carbon and oxygen, but it's definitely a lot of carbon, film by the side or coming out of the plume of one of these volcanoes. And it might as well have been the source for his sketch in his paper. So anyway, these are carbon films, and they're thin. And actually, they seem to just fold and flop around. And you can see it's almost like, it's kind of like bent and stuff. So we see a lot of this. Okay, so before I say something which is really rather shocking, and a reason why it's been a bit of a challenge for me this week, I just want to answer any of your questions. Do you have any questions? W. Hales reminds me of stellar nuclear synthesis. Well, essentially, yes. Like I say, iron is a hard stop. So if you're going up to iron and you have other things, and the iron is accreting on the outside, well, then you're going to get nuclear regeneration, and carbon's going to come out. So it's like you're going forward and then back, and going forward and back, and going forward and back. And it's only when you get rid of all less than 55% of the carbon that you then can push beyond iron, and so you can actually see the process. But I believe the process is happening in Lena. Everything points to it being the same process, and then you've got to argue yourself: is the sun actually working like this? Maybe we do. I know there's an argument that the various planets are actually hollow, and certainly, if, as it would seem, I believe that I've demonstrated that we can observe in the Lion reactor and in an X-ray exposed to the Lion reactor an identical structure, and we see this in multiple places, and the same structure is in European Space Agency images, exactly the same structure, several times, I believe, larger, or certainly in the same order of magnitude as the Earth in scale. One could argue that the sun is actually not a very large sun. If you look at something like Betelgeuse, it's vast by comparison to our sun. And I believe that on Betelgeuse you will see these same structures, which may be orders of magnitude bigger than our own sun. And so I believe these structures that are formed, these magnetohydrodynamic structures that are able to synthesize matter, like that, very, very quickly, using vast numbers of nucleons, you are literally having this churn of nuclear material. It isn't as simple as it's made out. It isn't this stepwise process. There is some forward and back going on.
Regardless.
And, so if those things are able to happen over various scales, and we see in multiple independent Lena experiments where we get these structures that are hollow. They're not always hollow, like I say. In the Slobodan Stankovic work, he could see there were layers and layers and layers. And it might be that you have layers and layers and layers build up to make a solid planet. But then the layers collapse in on themselves over a period of time and whatever. And so you end up with something solid. But conceivably, you could have things that look like they're solid planets, but they're actually a hollow sphere. That certainly, if we're extrapolating the orders of magnitude on the magnetohydrodynamic structures, then I would imagine that's possible. So is the carbon film white, or is that just a black and white image? They're all black and white images. And, I mean, they were all taken in 1997, so the equipment wouldn't have been as good as we have these days. And he does have some optical photography, and I'm hoping that, assuming nothing happens to him, that I can get access to whatever the photos he has, optical photography, and rescan those at the highest quality possible. And so that is my wish. Plans of mice and men. Well, why is the Earth pear-shaped? I think if you look at a lot of these structures that are in this data that I've just shared you, they're not exactly spherical, but they do tend to be spherical. It might be the larger they get, they become less spherical. So Axel is arguing that Evo is a dark matter which acts to produce elements at constant proportions for billions of years. Axel, I think you're probably right from the point of view that it's composed of dark matter. It's a dark matter. It's not necessarily dark. So first, in dark mode, it's dark, and it can be harvesting all forms of energy and making matter from that. And so it can convert dark matter into physical matter. And so since most of the physical matter is a very, very small proportion of all of the mass of the universe, there is a very large potential out there for many more stars and many more galaxies to be formed given the right amount of time, using the same process that we're observing in low-energy nuclear reactions. Yeah, bespoke matter, primarily, I think dark matter is potential matter. And so, like I say, exotic vacuum objects are, I called it the monopole clutch, but I was playing off Ken Shoulder's description of it being the universal clutch. It's able to convert matter into light, matter into dark matter into matter, matter into, whatever. Wherever you want to go with it. That's why I call it the God's toolbox. It does everything. There is nowhere to go from this. That's it. That's how it works. Corky, this is it. This is the whole keys to the kingdom. It's the whole keys to the kingdom, and it's amazing that Takaaki Matsumoto could hand round this stuff at ICCF 7 in 1998, and people couldn't see the significance of it. He couldn't see the significance. Why did he choose lead? Why is he specifically saying here? Why is he specifically saying here, perfectly carbon-free, eruption of carbon film from hollow lead ball? I mean, it's everything is there. Everything is there. You just had to pay attention. I will share some other slides from this same presentation where you have a lead ball which is solid, it would appear to be, and it spews out a hollow lead ball, and
then
they
we will
become
take a look at some incredible cutting-edge
one is hollow and
research
one
from
is solid.
scientists at
Now think about that for a minute. with your asteroids that seem to be like two balls stuck together. The problem with terraforming something like the moon is it has 1/6 of the Earth's gravity, so it doesn't have the gravity in order to produce an atmosphere. You have to have a planet that's of suitable size. Yeah, and Mars isn't big enough. Venus maybe, but you know it's. And then if it gets too big, then the atmospheric pressure's too large to support life. So you have to have habitable zone and the right kind of level of gravity to support an atmosphere, and in that respect, that is why Earth is such a beautiful blue globe that we live on, because it has this sweet spot. But there'll be trillions of planets out there with the right sweet spot. We just need to use this technology to get there. And if they haven't already got everything set up, ready to go for life, well, if they've got water, then I think you're pretty much good to go. You just need to, you can make electricity with the water, using cavitation, you can do what you need to do. So, you know, you can get the whole ball rolling with just those two technologies. So, Axel, I'm not so sure on the singularity. I do believe that you can get to all of the matter bar the balancing leftovers, which are either one proton or one triton, in a coherent matter volume of one alpha particle. Now, if the pressure is slightly different, then you might have many different coherent matter waves within the same overall coherent matter structure, as I discussed when I looked at the hole and the bridge on the Hutchison fracture sample. So I don't think a singularity is an infinitesimal point. I think it's at least those nucleons. If you push it further, then it's still something. It still has a dimension in there. Otherwise, it just comes out as light. I mean, if you go too far down, it's just going to come out as light. But I think most of these structures that you see will end up having a sphere which may have a broiling surface to it, you know, but it will be made up of subunits, and I will argue this in extreme detail when we are referring to the Vega Valley. But it's made up of subunits that shift around, they share their energy around, but the actual structure of that mesh, which Takaaki Matsumoto refers to as the itonic mesh, that itself is coherent. Do I believe EVOs affect gravity? Absolutely, they are have a relationship with gravity. They are pulling material in. If you look at Vysotsky and Adamenko's paper from 2004, they're saying it's gravity collapse. If you look at the early 1990s, in fact 1990 itself, where Matsumoto is referring to his ring spots, he's saying at that time that was quad neutron collapse caused by gravity. I don't know, have I got his book here? Right here. This is the front cover of his book in there, and it says on there, if I read it, miniban gravity decay of quad neutron. Gravity decay of quad neutron. Okay, and that's actually this structure. And this is from 1990. But this was his discovery, which in 2001 he says is not what happened. It's actually unmanageable numbers of nuclei in things that can be hundreds of micrometers across, and they all collapse. They can all collapse at the same time. Okay, so but in all cases it is gravity collapse. If you look at what we were looking at with Wheeler from his 1956 paper, I think it was, he is saying geons, which look like the structure that I derived from the Hutchison fracture sample, these tori, these kind of like electric and magnetic fields, the whole structure is held together by gravity. And so gravity, it's not just this is the interplay of gravity. It's what gravity is, kind of thing. I don't want to dwell on that. I'll talk about that when we come to the propulsion side of things. Your mercury arc experiment will melt any wire with... yeah, well, I think what you're getting is coherence there, Bestoic. What we found in the Vega experiments is they can sit there all day long doing nothing, but if you get the right energy at the right amount, then it'll just start consuming whatever the metal is. Doesn't matter whether it's tungsten or nickel or whatever. It'll just consume it. And it is very clearly consuming it on the very thin boundary layer, this inside surface of the double layer. And I believe that's where you have the electron degeneracy to the point where it's like a stiff balloon, and the electrons are all piling in and the matter's piling in from the outside, but it can't get any more packed. And so it ranges itself until everything is at the same energy, and all are in phase, and then that's coherent, and suddenly that starts to act as one big electron or one big whatever it is, and it can just chew up the matter around it. Okay, I'm just seeing if anyone had a really good question earlier on, just say I had one, and I'll go and see if I can find it. Otherwise, maybe I'll do a review of the questions after the next session in this presentation. I've got two things to make. One is really shocking, and the other one is some hot off the press data. When I say hot off the press, I have to share it now. It needs to be shared, and so. Okay, I'll just see if I can spot any questions looking up quick. Okay, Steve Whetstone, thanks for encouraging backup copies. I will pirate protect copy your fine video and arrange for re-upload. Okay, so yeah, so basically, I know a number of people are. If you get 4K downloader, it's a very affordable software, but I think it even works in the free version. You can download the channel, and I think just 1 terabyte drive. It doesn't need to be a fast drive. You can get the whole channel, all the videos on there. So people are talking about these craters on various places around the world and on other celestial bodies, including our own moon. What Matsumoto found is when a itonic cluster, a microball lightning, whatever, which is known to carry matter, and we've observed this, and Shoulders observed this, many people have observed this carrying of matter process, and the Russians have done the best characterization of its ability to carry matter. When that hits a surface, and if you can imagine that if it's still in the coherent state, then as it hits the surface, it's maybe a little bit superfluid, but it kind of like maybe impacts. And what Matsumoto found was over a period of time, it would kind of spread out over the surface and leave a mark, and the mark was hexagonal. And so it could be that there are things that hit these celestial bodies that you wouldn't necessarily even observe them on their way there. They just hit them and then spread out. And it might have been in very energetic events in the solar system that caused this. And, you know, you might just see like the glow on a planet, but you wouldn't necessarily see the incoming thing. That's not to say you wouldn't if it was in a white mode, or it was interacting with the solar wind, for instance, and that was exciting it. So, but certainly Matsumoto, and maybe I'll share those. I think it was a certain energy magazine in the 1990s shared some actual color images of microscopy. So I think I'll dig those out and share those. Okay. All right. Well, if you have any questions that you really want answered, and I will do my best to answer them, go to remoteview.icu, look at the newsletter entry for this particular video, and put your questions there, and I will endeavour to answer them. I think what I need to do now is talk about something extremely serious. So, we've had a debate within the project about how we get out certain information, and there are more than one director in the MFMP, and we can't be disrespectful to the issues should someone do something stupid. And we have had an unimaginable amount of different approaches to try and destroy the project. I've talked about this in the past to some degree, but it's much worse than you can possibly imagine. And no one wants to be in a position where someone is encouraged to do something stupid, or doesn't do something stupid, but is portrayed as having done something stupid, and then that is used as a pretext to shut us down by lawfare, i.e. it's not like there is any truth to us doing something that caused someone else to do something, but it doesn't matter. They would use the lawfare to cause a problem for us. So I've been trying to the very first video that we took, and you can go and look at this on our channel, go way back to 2012. Francesco Celani was the first man to have courage to share his technology with the MFMP. And if you look at that very first video, he says, you know, I'll be happy to share it with you, but the most important thing is safety, safety, safety. Now, why does he say that? Well, you just have to look at PAP. I described in my monopole clutch video what I believed was going on. Basically, it was producing exotic vacuum objects. The very thin wire that was connected to the mains was acting as a ground wire for those EVOs, so they didn't build up in the metals, in the pistons. then the wire was pulled out by Feynman. Feynman then refused to put it back in when Pap was demanding that he did, because the device was starting to shake and becoming unstable in his view. And in Feynman's own account, when the cylinder head blew up, a silvery white object shot out and turned to a white puff of smoke. And I would believe that that was potentially, if it was made of this, the actual cylinder head, the piston, and that would have maybe been made from aluminium, and that would be super loaded with exotic vacuum objects. The whole thing would be instantaneously turned to a coherent matter blob, as we know aluminium tends to do quite easly. It's one single isotope, 27. And as I said, George Eagley, he had a ball lightning thing where they came down and touched the window frame of a train, and the account was the person could manipulate the aluminium for about 20 minutes before it set hard. They were able to cast in 1992, in Tom Bearden's book, it's recalling this, the Russians were able to do cold metal forming using some electromagnetic means. That there was John Hutchison, of course, being able to do this. So ball lightning, and there are other examples. Ralph Ring talked about it when he was with T.L. Carr. So I believe that that's what happened. And when it came out, there was a Coulombic event with oxygen, and it instantaneously oxidized the aluminium to aluminium oxide. And that accounts for Feynman's own account of what happened in an event that killed multiple people in killed at least one person and maybe two, but I can't remember that, but at least one person died, and it maimed severely some other people there, and there was a legal case and so forth. I know that a very serious event had happened in the mid-1980s with Pons and Fleischman, and that, I have argued, was an exotic vacuum object coherent matter formed out of 1 cc of palladium with deuterium, and then that exploded and went through and vaporized a load of concrete in the room and so forth. I believe a similar event happened with Mike McCubry at SRI, and a person was killed there. It's put down to a hydrogen explosion by some parties. I believe a coherent matter state was formed, and it caused a very unfortunate incident. And I believe that when I was with Suhas Ralkar, you can go and look at the Steemit channel. There is a thing called brilliant light shower, and what it was is that every so often we would have these massive flashes that gave out this sort of blue, like kind of like you would get off a black light, UV light, and it would fill the entire room, incredibly intense. And in a good number of those events, the huge industrial three-phase power supply would trip out, and I think that was a coherent matter explosion, EMP. And the fact that these exotic vacuum objects can, in the case of aluminium, make them soft, but in the case of iron, like you might imagine that the actual engine was for PAP, it just causes it to split like it does with John Hutchison iron-based materials. And I've argued exactly, in my view, why that occurs. So if you let these things build up, there's nothing that will stop them. Now, in the second part of this presentation, I will share unimaginably amazing data that supports this hypothesis by Yul Brown of what he was reporting in the public in 1988, and what is reported in this work that I'm sharing with you tonight from 1998 by Takaaki Matsumoto. I think it's an absolute slam dunk for both of those, and that we can synthesize elements. And so this brings me to the reason I brought this data forward rather than doing some other things is because we've also experienced an explosion, which may have been a coherent matter explosion, but it was definitely an explosion. It was called Bang, and it was with lithium aluminium hydride in nickel, and I think it was in early 2015 or early 2016. So you can go and look at Bang on our channel. So I've experienced a couple of occasions. I've also experienced the person that made the supernova reactor. He was 40 years old. He died, I was told, I believe, by cancer, breast cancer. He left 2 young children and a father, and his wife. And so there's that. And I've seen Norris Peary and so forth. So with that being said, I have was told this week some unbelievably shocking news. Roy Shinamaza has just got out of hospital, and thankfully he's got through what happened. When you see me in Japan and I'm wearing whatever safety glasses I could get, and I didn't know much about HHO, but I did respect it because of what I'd seen with the various experiments of Suhas Ralkar. I knew it needed to be respected. But what happened was, this is the story I was told earlier this week. Those people that know how to do HHO, they will have a backflow, and this is kind of like a device to prevent flame propagation from the nozzle through to the chamber in which the gas is being produced. I am told that for whatever reason, and I actually asked when I was going down to do our tests, have you got like one of these devices on there? And I was told yes. This wasn't put on, and there was a catastrophic explosion. Roy Shinamaza survived, but one of the people I was working with there was killed. You can't mess around when you're dealing with something which is so powerful. This is not a joke. When I say this is the God's toolbox, and you know what I think about what this can do, you cannot mess around with it. Even before this week, we were saying, legally we have to say you can't do this at home, kids. And I said, well, what can we publish it in a scientific paper? Or can we put it into a patent? I mean, there's lots of patents out there. There's a patent for a knife sharpener. If someone makes their own knife sharpener based off a patent, and they get it wrong or they don't use it properly, and they cut off their finger, are they going to sue the person that applied for the patent? I mean, how do we deal with the fact that we simultaneously have an unimaginable amount of people wanting to shut us down, and it's provably by people that know and could command the people that wanted to shut us down, something that has great energetic potential. And I have that ringing in my head from Francesco Celani in 2012 in South Korea. Yes, you can try and replicate this, and I will help you. But the most important thing is safety, safety, safety. That was long before I knew about strange radiation. That was long before I knew that this thing could go into your body and it can change your DNA, can smash up your DNA. Now, mainstream, they just try and explain everything with it's just a hydrogen explosion. No, it's not. This is much, much more interesting and also much, much, much more powerful. And it works in very, very different ways. Coherent matter is, it's the toolbox, it's the God's toolbox, and it has to be respected. So I'm really, really sorry for the person that's died. And I'm sorry to Roshan, because I'm trying hard to get all this information out. I'm trying. And it's so amazing. It's so amazing what I'm going to share in the second part of this presentation. But don't just go out and get yourself an HHO unit and start doing stuff. Because it's very dangerous. Okay, okay, I've got something. This is from the Vega Valley. It's the last presentation slide that I have for you today. I would have liked to have had a full map to share with you. But it's tough to get people to do things, and it's been even harder with the cold that's been going about and all the nonsense that that's caused. But I have to thank Alan Goldwater again for doing this, and I'll have a whole separate presentation for sharing the data that we already have as soon as I can get through it. But already with what I'm going to show you now in this one slide, it is amazing. It's absolutely amazing. It does need for us to be able to see where these things are occurring. But I believe that the Vega Valley is a coherent matter structure. It's a aggregation of that structure, and I will talk about how that comes about. And I will do my best to explain the formations that some of the formations that you're going to see that you've already seen in video, but you're going to see them in unbelievable detail. So without further ado, I will share that. So this is the Vega Valley, and I've just done this composite image of a whole bunch of things. And we are looking here. The brass is maybe a light brass. We'll know when we do the full proper analysis, but I think it's probably around about 80% copper and 20% zinc. This is the valley channel, and these are the valley sort of edges. And we speculated that maybe the black areas on here, these black areas were carbon rich, and whatever is going on in the center is whatever's going on in the center. When you look at these structures, they are almost like an artisan's brush. I would describe these as like those temples in Cambodia. They are self-similar. So you have a big one, and then the big one has half attached, like these things seem to do. They're half on. And on those substructures, you again have substructures on those substructures. It's literally like those watts you see in the ASEAN Peninsula. And they do appear to be hollow to a degree. So they seem to have this very smooth structure on the outside, but inside they are hollow. And the tips, if we look at 2046 and 2047 here, they are, by atomic concentration, 56.9 and 24.99. What is that? That is 80 point, well, 82, 81. Very, very close towards the tip, as we've observed in 2 other different data sets. The copper is vastly reduced. This should be 80%. And the zinc is, it could be just 10%, but we're going up to 16% here. So it could be that the zinc is reduced, or that it's just relocated, or whatever. But certainly the tips in both of these are very high concentrations of triple alpha and quad alpha. And you see the carbon goes down here. The oxygen's gone up a bit, so we've got what, 60, 74. It's a little bit lower, and the thing that seems to be increased when this is lower is the copper and the zinc a little bit. In fact, more the zinc. When we go into the sort of puffy, fluffy area, which is apparently a little bit hollow, we have much lower carbon, around about the same, but lower on average, oxygen, but much higher on the copper, and maybe 16. So this actually maybe, if this is closer to the original material, you could maybe argue that it had 16 zinc. But we will know when we look at some of the material that isn't affected. So the hypothesis that the blacker areas here were carbon rich is borne out by the SEM data. And we've done all kinds of line gradients and so forth. So I can tell you now that if we were to put a line from here to here, this tip would have the highest carbon, and then it would go down and go down here, and then this tip would have a higher carbon than the area here or the area here. So these really are, in my view, they are self-similar, self-organized structures that are driving what you are seeing here. And they are highly aligned, as we saw in the microscopy and in the macro photography and videos that I've shared. Now, this is another fragment that came out of the sample. Now, all of these fragments that are being looked at here by Alan Goldwater, they are from the sample. If you go, there's a video where I actually knock off a few bits and I look at it under the microscope, and some of them are like jumping around a bit. So you can actually go and see, and maybe you can even find these particular bits that are shown here on this composite shot. But what I find very interesting about this lump here, and I said that this area here, this kind of area here, is very brittle, and there are different forms of it as you go up and down the valley. I don't know whether this bit here is coming from an area like this. It may or may not be. But this is why we need to look at the whole sample and to see if something like this appears somewhere else. I suspect it does. And I'll tell you why I suspect it does. Because look at this. We have 73% carbon bioatoms and 25%. So that's 80, 70, 80, 90, nearly, God, it's nearly 90%, isn't it? It's more than that, isn't it? 98%. It's a lot. It's a lot of carbon and oxygen. But you know what else is there? It's calcium. And look at it here. 76%, 10%, and then 7.39% calcium. Now, every single one of these sample spots has copper and zinc. So one might conclude that this is something to do with this sample. The one proviso I have is maybe these were in the same sample container and there was a little bit of copper and zinc that broke off some of these and contaminated these spots. But anyway, that aside, if we are to assume that this is some of this brittle material, then what it's done is it's converted it into triple alpha, quad alpha, and dec alpha. Okay? and there's nearly no copper and zinc left. Okay, but it's not just that. If you look at what you see here, you have these magnetohydrodynamic structures, these circular structures in here, and this one's got like a hexagon structure around the core with a hole in the center, a hexagon-like structure around the core with a hole in the center, and they're sort of spaced semi-regularly. So I cannot wait to get and inspect this, and it's just frustrating that it's taking so long. It's just frustrating. But here we go. I believe that this supports everything that we've said in the video above, and that whether the Evo is in here or whether the Evo is in here, whatever, I believe that this is due to coherent matter, and it's self-similar and self-organizing. So with that, that is your lot for tonight. Does anyone have any questions? And I'm sorry for the grimness there, but I think it's I have to say it really. It's just the truth. So in terms of our own approach to the brown gas generator, the intention was to hire a 20-foot container, put it in there with in and out venting, out in an outside space, and have a long hose and remotely turn it on and off. And the testing would be done some distance from that contained generator. So we already planned for this, but it really brings home the nature of what this is. It's one thing to hear in 1988 or read that a piece of newspaper article in 1988 or a journal or a magazine article is saying that this is able to convert pretty much anything to carbon. And to have seen that in many, many experiments, it's a different thing to really come to terms with the fact that this is the God's toolbox, and it's able to change matter into light, and light into matter, and dark matter into matter, and matter into dark matter, and all of the above, and that can be done in a way that is almost imperceptible, and it can be done in a way that is highly, highly destructive, and so. It might be that the pressure is the thing that kills, but it is the fact that containment can be completely negated by exotic vacuum objects, as I believe happened in the PAP engine when the bleeding through the ground wire was removed by Feynman. Yeah, The Ultra experiment is just wonderful in terms of safety in level, because they run very short period of time. They're open to the atmosphere, you know, and it's a very special thing, that Ultra experiment, and those things, they can only run for like, I don't know, 360 seconds a go. So you have to be working hard to drive it for too long. We can learn from this. I mean, like I said, we were prepared for doing our Brown's gas testing. In fact, on the team, we have one of the world's best HHO operators in Slobodan Stankovic, and so we will be using his experience when that comes about. But I want to be able to confirm what I'm going to show you in the second part of this video presentation set, because it is just mind-blowing. It is. I've already shown enough to show that a Mars gas is LENR in a can. It's low energy nuclear reactions in a can. It's like a few seconds and you're getting unbelievable transmutation. And it's not that it does, it just follows the same patterns every time. And it follows what Matsumoto showed in these images that I showed tonight, particularly the ones where you have, let me go there, particularly these ones, where you have this plume coming out of the ball. You will see this, and you will see something similar to this, and you will see something similar to this, and something similar to this, and it's so clear, and there's more, because it doesn't only necessarily produce just carbon. If it's pushed harder, you get silicon and so forth. So you will see that in other slides that I will share from him in the second part of this presentation series. What do you think of the structured atom model? I actually really like it. I've met both of them a couple of times. I've spoken with them, conversed with them. I have no problem accepting that the neutron is just an electron, and the proton is proton electron make a neutron. There is that balance of the neutrino or anti-neutrino depending on which way it's going. That's not something that they consider because it's not really necessary for their model in terms of the structural part of it, and it also kind of feeds into why large structures fall apart when you destabilize them by interacting with the available electron quanta within their structure. And so EVOs like electrons a lot. They also like ions a lot. And when those things are coherent and the ions come in, well, you know, it's what was formerly thought as an immovable object being met by a truly irresistible force, and the irresistible force will just remove that Coulomb barrier and remove any barrier that prevents it from consuming those nucleons. Okay, question from Steve Whetstone. Would an NMRI, nuclear magnetic resonance image 3D scan of these materials be helpful? Yes, it would. Well, yeah. Anything that could look at the internal structure of them would be useful. Yeah, of course. Absolutely. All analysis would be good. I mean, when the university up the road said, "Oh, can we look at the Vega Valley, and we'll need to cut it, and then we'll need to wash it, and then we'll need to ultrasonically clean it," and I'm thinking, you are not putting this in any ultrasonic tank. Firstly, you don't even know what ultrasonic can do, and secondly, it's brittle. He'll smash it up, and I want to see where everything is. I don't want to clean off the carbon or whatever salts there are on there. I want to know what's on there. That's the whole point of leaving it exactly as it is. I cannot get through the ethical considerations to make this safe and transmutative for society. What giant steps are needed? If I was Musk, I would need to know this. Forget the DC dopes. We've argued firstly, in terms of the Vega systems, there's as dangerous systems being shared on YouTube all of the time, but those people are not targets because they're not doing almost in every case they're not doing anything that is dealing with what this technology can do. They might observe things that this technology is doing and interpret it in a conventional way, but they're not targets for takedown. So, and I don't think the argument would wash with saying, well, look, they could have looked at a number of videos. Now, one argument could be said is that if you want to build this, what you need to take this video that's already public on YouTube, this video that's already public on YouTube, and this video that's already public on YouTube, and bring them together. But don't do it, kids, because you're going to kill yourself. Just don't do it, ever. Don't even consider doing it, okay? It's our recommendation you don't do this. But by the way, if you did, it might do this. You know, if someone was competent enough to do this and take all the right precautions, this is probably what they would see. But don't do it, you know, that approach. The other approach is you put it into a pattern, like, you know, people can build a Wardenclyffe tower based on the patent, and it will produce voltages that will kill anyone, right? Obviously, you can't go and legally challenge Tesla because he's dead. But there are many, many patents out there that are published because they need to be published, but they describe things that can kill people. So, you know, we need to have a strategy. Dave, I will talk about PAP at a different time. We have a device which is going to be open source again, and again it's this challenge to create the sparks, and I have a deep understanding which I will share, and it's again the same thing. The person that's made the spark is, in my view, quite close, and he wants it to be open. Again, this is a thread that we would have started last year had we already verified Amaza's work with Brown's gas generator. But whatever, I think so much has been able to be done without that. It's you know, we're all moving forward. So about Fix Fukushima, ultrasonics will do it. Brown's gas, Amaza gas will do it. One thing that's interesting that's come out of the conversations I've had with my Japanese colleagues this week is that the younger chap that we work with, who actually held the Amaza torch in the videos that you see when we are testing Amaza gas in 2019, he last year went to go and work at Fukushima. So I believe that there is a reasonably good chance that even if we don't actively get involved with fixing Fukushima, he is capable of allowing or enabling that technology to be used. Okay, so I think it might be a case of our work here is done. What we need to do is to try and force the function somehow where they recognize not only is the tritium water, those 1.2 million tons of tritium water, laced water, is not only fixable, it's a valuable resource. So for instance, if you go to the reaction calculator for at nanosoft.co.nz. In fact, we'll do that now. Let's do that now. I'll get you a reaction here using tritium, and you can get two birds with one stone with this. It's a wonderful thing when you have tritium. Okay, so right. Let me get this for you. So the first one here is, if you take tritium and antimony, you can make tellurium, which is 11 times more valuable. If you take tritium and tungsten, you can make rhenium, which is 100 times more valuable, or bordering on 100 times more valuable, by using tritium and tungsten. If you use tritium and plutonium, which is probably the worst non-beta isotope element. I think there's an isotope of chlorine which is really nasty, but plutonium is really nasty, 239. It will preferentially produce thorium-232, and we know that that comes out quite easily because thorium-232 is really quite an abundant element. So that would fix plutonium, and you can use the tritium water with exotic vacuum objects and plutonium, maybe in a cavitation process, to synthesize thorium-232. And you get 15.89 mega electron volts out of that. So you get rid of two really nasty things, with plutonium being the worst. So there are options. You can go on nanosoft.co.nz and run these reaction tables. And as I've discussed them here, I'll probably post them at the bottom of the blog, the reactions you need to do to find that. So, WP for Truth. Hey, Bob, do you think an EVO can be created at the very low level of voltages? Yes. That would allow full control over motion and field strength, or is that the ultimate goal? What is a low voltage? Matsumoto was achieving this with 120 volts. Is that a low voltage? I think it's low enough that it doesn't kill a lot of people. So yes, I think if you have the right voltage with the right ability to have an ionized gap, and the gap is close enough, then you can have EVOs produced every time a spark is produced. So if you have a low voltage discharge with a very small gap, you can get EVOs produced then. So yeah, you can produce it at very low voltages. It's the volts per meter, and so if you have like 1 volt, but the gap is like 1 nanometer, that is a very, very, very large volts per meter. So you will have a chance to produce EVOs in that. So it's not the voltage per se, it's the volts per meter and the ability of the material, its work function to release electrons. Maybe its temperature. I mean, you can have thermionic emission and other types of emission, which I've discussed, and we'll go into greater discussion in Something Electric Part 2. But if you have a point as well, so if you have a point and the point is hot and you have a very small gap, and you can have a very low voltage and still produce exotic vacuum objects. Great, WP for truth. We need every solution possible. You said you got some sketches for potentially for Fukushima. Yes, WP for truth. Go ahead to break up things that you need to break up. Some of my videos are long form and some of them are short form. In a way, I like doing these long form videos because people that might want to do us some disservice are likely not to be bothered with going through the hassle of watching the videos. Compounded on the fact that they haven't got the backstory. So it's kind of like... I can throw a toaster in some bath water. Does that mean we should ban all toasters? Yeah, right, exactly. Mighty Mouse Girlfriend, did you want me to sing Unchained Melody? I need your love, darling, need your love. Yeah, you were talking about firearms. Okay. Thanks, WP for truth. Gordon Doherty, tritium and plutonium, maybe not a good idea. Not normally, no. It's about critical mass, isn't it? Normally with plutonium, you have to have a large amount in a I mean, in fact, I think with plutonium, you know, as long as you're not breathing it in, because it has a slow half-life, you can actually hold a block of plutonium. You need to actually have an explosive that compresses it and gets it above criticality. So the idea of having a plutonium salt dissolved in the mass of tritium water or tritium laced water and then cavitating it, you're actually interacting a number of atoms, you know, together. So I would certainly, I'd certainly not want to run those tests. But, you know, in theory, it should work. And quite likely, you wouldn't get thorium out. Mostly, you would probably get more carbon out. Yes, W. Hayes, this is kind of what I'm saying. The second reaction you actually get from tritium and plutonium is uranium-235. So you can turn something that's really toxic into nuclear fuel. In fact, those are the only two options. You get thorium-232 or plutonium or uranium-235. And I think whatever it is, helium out, is it? Yeah, it's you get boron 10 and 232 thorium, or lithium 7 and uranium 235. Yeah, the key is the time it takes to produce the spark. A nanosecond spark, no matter how weak, will produce evos. Any spark, no matter how weak, will produce evos. Steve Whetstone, has anyone used resonance matching current flow to the NMRI frequency? Not that I'm aware of, but certainly MRI has been used to, for instance, look at iron 57 production from manganese 55 using deuterium in methogenic sea ooze for experiments by Vysotsky and Korlinova. Good one, Bob. Bore the enemy. You see through my strategy. There's two options: the crazy Bob or the boring Bob. Did you ever put any strange radiation detectors on your samples to make sure it's safe to sit near them all of the time? I do what Parkhomov does. He says he keeps long distance between him and his reactors when they're operating, and that's essentially what Shishkin does. And Shishkin has calculated next to his cavitator 1 hour exposure will kill a man, and a shorter time frame, I think it was enough to nearly kill Leclerc and his partner at Nanospire. So the thing is, if you have a cavitation system where the cavitation location doesn't change, it will build and build and build and build and build and build and build. To a certain degree, that's kind of what I believe is going on in the Ultra, but because the experiments are short and because they're not so static, the foil, and it can move around, and the foil is thin enough to fall apart, and then that's the music stops at that point. You're just getting to the point where you're producing, it would appear, those iron crenellated spheres, and more work needs to be done to verify for certain that they aren't in the rolling mill process or somehow contamination. It's definitely not from the steel in the chamber for the ultrasonic tanks, because those contain chrome and so forth, so it doesn't have the chrome in there. So and because we've seen it in so many other systems, including natural ball lightning, it's very likely that that is actually being produced in the cavitation. Bob, do you expect more details on the accident in Japan with Omasa? I hope so. I don't want to pressure him. He's just got back out of hospital. So from my point of view, I think I'm absolutely shocked to the core that someone has died. Another person that I have worked with has died in this energy space. The statistics aren't good with the small number of people working in this field. The fact that Omasa has survived, the fact that Omasa has been so mortified. I would have been so mortified if I had not shared the analysis that I've done of the samples that we tested when I was there. Other than they were on my poster at ICCF 22, but they're not sufficiently public in my mind. The people that were ICCF 22 saw them, and I discussed them, and you can see me even discussing them in my off-piste presentations, but they're not fully in the public space. And I'm very conscious of, what lengths had to be gone through, so I could share you a couple of slides over this last week from Matsumoto that were shared and tried to be publicly put into the public sphere in 1998 by Takaaki Matsumoto. He was trying to share them and no one cared. But unfortunately, Matsumoto didn't have the access to YouTube. It wasn't really a thing as it is now. And there wasn't the awareness. So I feel a deep sense of responsibility to get that out. And now that... God, if he had died, I'd just been, oh my God, I have not been able to share that data, and he's passed. And this for me, the allowing me to go and test that for and for him not to get that data, it would just be a travesty. Yeah, you regenerate the spent rods. Yeah, well, I would suggest, and I think it's you get tritium. Well, yeah, I mean, you're using the tritium waste and polonium-239, and you get 7.7 MeV, but it's 15.89 MeV for the reaction that produces boron and thorium. And thorium is so abundant in the Earth's crust. There's many elements that people use industrially that are, like, for instance, I think tungsten, for instance, is something like 4.5 times or maybe even 6 times, but I think at least 4.5 times more abundant than thorium-230. Sorry, less abundant than thorium-232. Thorium-232 is 4.5 times at least more abundant than tungsten. Okay, and we use tungsten industrially all over the place. So given the fact that it's abundant in the crust, and given the fact that it's more than twice the energy yield reaction than that goes to uranium-235, I would argue that most of it would go to 232 thorium. That being said, we have shown in a Mars's vibrator system that you will get bands where what I call the compression or decompression of the physical vacuum will yield bands of elements. So I expect that there will be potentially some production of uranium-235 alongside the 232. And the uranium-235 in the processed, firstly you're taking a really unpleasant nuclear material.
Cataclysm has this portion of the island
in plutonium-239. Just unimaginably unpleasant. I mean, no one knows what to do with it, or at least that's the theory we're told. And they put them in the ground, and like they say, I think who was it said, no one knows how to store or effectively store solar energy overnight or wind power energy overnight, although there are options with compressed air and so forth, and potentially with battery technology, but not really that effective, or pump storage systems with hydroelectric. But everyone's expected that something that has a 232,000 year half-life or whatever, 250,000 year half-life, you can store that in the ground and no one's going to dig it up before it's decayed to stability. It's just not going to happen. We need to have a solution, and this could be it. The tritium could be the solution, at least for a small amount of it. So Gordon, thank you. Good night. I'm going to call it a day, I think. Just see if there's anything. I built my own hydrogen torch. Yeah, probably. Okay, so yes, you've got to have a flame arrestor. Yeah, it's so energetic. Okay, good night. Okay, thank you, Zignal. Okay, so that's it for me tonight. Look out for, at some point during the week, I will either do a pre-recorded or maybe a live session, but of the second part of this presentation. It's going to be absolutely stonking, because the data that I have from that Amasa gas testing, particularly, well, I mean, the thorium's amazing for a different reason, because I verified it with the filter capturing the vapors, but and that's not been done before. But the choice of using one of the lowest melting point elements that doesn't ignite in air in the choice of indium, and the fact that the indium was the thickness of a human hair, and it was it's also, I think, 97% a beta isotope. These are the reasons I chose it. It was like the most extreme opposite I could think of that I could test that was a beta isotope than tungsten, with its low melting point. It's like 152 degrees centigrade or something, barely above what we measured the gas flame to be. So with that, I look forward to seeing you later next week. Or later this week, as it is for me now. Thank you for your time, and just everyone give a prayer for the departed. I don't want to dox his name, but just if there's one lesson to learn from tonight, is that we must respect this technology. It is unimaginably awesome. So thank you very much, and I will see you in the next video.
Leave your comments for posterity. Very few have seen this and it will be famous one day in the future and watched by many. Check the live discussion comments for links to great videos during the show live discussion. Leave your comments on the YouTube page if live discussion is over. Be encouraging. Donate money if you can please. Upvote and say thanks with your time if you're poor like me. THX link to this video discussion in Solutions for Earth Catastrophe Cycle on Facebook at https://www.facebook.com/groups/Solutions for Earth Catastrophe Cycle 2048/permalink/8648302910811716/number Straw Hat Ford Pirating.
Hi, my name's Bob Grinier and I'm a volunteer with the Martin Fleischman Memorial Project. So I hope you can all hear me. Thank you for waiting and being patient today. I will explain at the end of this presentation some things that have happened over the last week which have resulted in a slight adjustment of priorities, let's put it like that. And I also have some incredibly beautiful data to share at the end of the presentation as well. So stick with me for that. Anyway, it's good to see you. Yes, fantastic, you can hear me. So this is Tree of Life Part 1, and this slide has an image which is a panel. I think it's from Iraq, from the sort of Sumerian art sort of lineage, and it's I don't know whether I'm going to say this correctly, but it's a Phrygian panel closely following the Sumerian tree of life, and apparently this is from around 600 before Christ. So if Christ was able to go into the desert for 18 years of his life in this region, could he have learnt some of the tricks of the trade from these people? Who can say? It's the 23rd of May 2020, and I am going to try and talk about how exotic vacuum objects can actually do real work. And there is a lot of interest in being a multi-planetary species, and I believe that that's what we already are. But anyway, if we are to go to other planets, we are going to need to be able to ensure that when we get there, we have all of the elements for life. Well, we have all of the energy when we get to a planet because it actually has matter on the planet. But can we use that matter and convert that into elements that support life? And if you have water there, well, I would argue that you can, because from water you can create a charge differential, and from that you can create other elements, and with other elements you can create electricity, and from electricity and other elements you can create all the elements for life and more. And so I think I'm going to start that argument here. The actual image that you see here, this panel, is something I took off a slide which I had in my Sochi presentation, because it's actually from a slide from Ode, and this was one little element that I left out, which you'll see the full original slide from Ode in this presentation. So what am I going to talk about? Well, firstly, I'm going to talk about the fact that carbon actually is quite a rare element. So if I get rid of my mugshot there, if you look at the Earth's crust, that is, if we start with the Earth's crust, and we look at the elements here, and I'm going to go back to my mugshot, and I'm going to change my mouse so you can see me pointing. Let me just do that. I should have done that before. Preparation prevents poor the other one, and we'll do that, and we'll put the silly large cursor. Okay, right. And we're back in the presentation. So we have a big cursor here. And now if you look at the most abundant elements in the Earth's crust, well, top of the list are oxygen and silicon. And in fact, they account for, let's put a quick calculation here, they account for 40, 50, 60, 72.3% of all of the nucleons in the Earth's crust. And then aluminium, who everyone worries about as being something that's really rare, well, actually it just binds to oxygen really, really well, so it takes a lot of energy to produce aluminium. But actually it's the third largest concentration element of abundance in the Earth's crust. And if you add that to your 72.3%, you get 80, over 80% of the crust is these three elements, O, Si, and Al. Add in iron. Now, of course, iron is more in the core, but we're talking about the crust here. That's the bit we live on. Fortunately, we don't live in the core. That would be uncomfortable. And then if you look at these other elements here, calcium comes in at number 5. Okay, and this is going to be relevant as we go through a discussion moving forward. But obviously, you can't have bones in your body without calcium. Oh, that's my mess there. Would you look at that? That's a treat for you. You can't have your body bones, and you can't have calcium carbonate. You can't have seashells all kinds of things rely on this incredibly abundant element here. And calcium is double magic. It has 20 neutrons and 20 protons, which means it's extremely stable. So if anything was to transmute to calcium, it's unlikely to transmute away from calcium, or it's less likely. So we actually find calcium in many, many linear reaction systems, and I believe the crust is a good way to know that that is something that we should expect. And that is, again, 4.15%. So in terms of the crust, calcium is bordering on very close to the amount of iron there is in the crust. And so it's very likely element, in my view, to be created by exotic vacuum objects. Then, of course, sodium is important, as is potassium in our blood for, we're a saltwater creature. We don't live in the sea, but our blood is basically salty, and we have salt in the form of sodium chloride and potassium chloride. Magnesium here, we see all of these elements often produced in low-energy nuclear reactions. And hydrogen here is actually, it's quite the way down the list. And considering hydrogen and oxygen up here are so important for life, then why is this down here? Well, basically hydrogen is a building block, and you'll see this as we go through this presentation. And phosphorus is very important to life as well. Manganese less so. And then we've got down here sulfur, very important to life, and there is carbon at the bottom of this list. And look at the proportion here. It's 0.02%. 0.02%. So, when you compare all the other elements above it, this is a relatively rare element. And so, it's a precious resource, and people think of carbon dioxide as a terrible thing in the world. But actually, if we didn't have carbon, we couldn't exist, and neither could plants. And so there we go. Right, so where is all of these elements coming from? Well, if you were to look at the public data on this, there are two things that are going on supposedly in the sun. And one is the carbon, nitrogen, oxygen cycle, and the other one is the triple alpha process, supposedly. Okay, and we're going to read this little clip here from Wikipedia. This is the official accepted understanding. Unlike the proton-proton reaction, this is this PP chain up here, which consumes all its constituents. The CNO, or the carbon, nitrogen, oxygen cycle, is a catalytic cycle. In the CNO cycle, 4 protons fuse using carbon, nitrogen, and oxygen isotopes as catalysts, each of which reaction. This is this PP chain up here, which consumes all its constituents. The CNO, or the carbon nitrogen oxygen cycle, is a catalytic cycle. In the CNO cycle, 4 protons fuse using carbon, nitrogen and oxygen isotopes as catalysts, each of which is consumed at one step of the CNO cycle, but regenerated in a later step. The end product is one alpha particle, a stable helium nucleus, for those that don't know, and 2 positrons and 2 electron neutrinos. Now, what you have here is the so-called log T. This is the temperature, and this is the log energy that you get out. And the sun apparently is about here. And it's just at the bottom end of the CNO cycle.
Steve Whetstone, founder of the HOEP project. Very smart, no money, lots of solutions for solving world problems.